Morning, my name is Mohammed Zamira. My roll number is 219518041. Today's subject is vlsi. I am from ECA section. Today my topic is real-time fault detection and diagnosis system for analog and mixed signal circuits of acoustic. Introduction of fault detection. Fault detection is critical in maintaining the reliability of analog and mixed signal circuits. Acousto-optics deceives devices are particularly sensitive and can exhibit faults that compromise performance. A real-time system is essential for timely identification and resolution of these faults. Important of real-time systems. Real-time fault detection ensures minimum downtime in circuit performance. Quick diagnosis can prevent extensive damage and costly repair in complex system. Continuous monitoring allows for proactive maintenance and improved system longevity. Introduction. The electrical power system EPS is a complex network of power generation, transmission and distribution that provides electrical and end users. Recently, EPS has become more complex due to the renewable generation, electrical vehicles, energy storage system and smart grids. A critical challenge in operating EPS is maintaining the stability and quality of the delivered power. Power quality disturbance PQD causes due to various reasons including equipment malfunction, weather condition or issues in electrical lines and causes and emotional losses. Moreover, EPS damages caused due to a fault increase over time. Hence, early detection of type and location of PQDS is important to mitigate the effects of PQDS, protect and restore the EPS, and prevent cascade damages. Power quality in EPS is monitored by measuring voltages and current signals, and there are several standards and protocols to detect PQDS based on the measured power quality. One of the widely recognized standard for PQDS is IEEE 1159 standard. This standard provides guidelines for monitoring and analyzing PQDS in EPS. It covers a range of power quality issues including voltage passage, voltage swell, harmonic and interpretation. The IEC 61666 series is also known as well-known standard for managing EPS, providing guidelines on the power system design, installation and maintenance of EPS to ensure that it meets acceptable levels of power quality. Although these standards suggest reference values for various fault scenarios, it is challenging to establish protocols that cover all fault conditions due to the complexity and non-linearity of EPS. Recently, deep learning has been proposed as a potential solution to overcome the aforementioned limitations. Deep learning, a subclass of machine learning, techniques has been rapidly developed and demonstrated to capable of analyzing both linear and non-linear systems without manual features extraction or optimization. This is because deep learning is capable of training a model from data in the field of PQD detection in EPS. Various deep learning models including convolution neural network, CNN, cursive neural network, RNN, long short-term memory, LSTM, and autoencoder have been proposed to enable accurate fault detection via deep learning. Our previous work proposed that the deep learning model can accurately detect EPS faults. We demonstrated the feasibility of the proposed idea via of a deep learning model consisting of several convolution layers, fully connected layers, and synthetic layers. Although this work successfully demonstrated the proof of concept exploring deep learning of PQD's detection. The data used for training the deep learning model had voltage information before and after PQDs, indicating the method did not enable prompt action for predicting the power system from PQDs. This is also why many previous works utilizing deep learning from PQD detection could not perform real-time operations. In study proposed a real-time method for detecting PQDs in power system as early as possible by harnessing the data segment approaching with transformation based of deep learning models despite of schematic schematic the voltage and current warmers oscillates over time at frequencies of power generator in the power system. When a fault occurs on a certain line or bus, there are significant fluctuations in signals in power system. Segments of electrical signals are fed into the deep learning models as inputs to identify the fault type and location. If there are abnormal signals in the segment data, the deep learning models can detect fault conditions, enabling promote PQD's detections method, which cannot be achieved when using the entire voltage signal as input and deep learning. In summary, the main contribution of the present work are small segments of voltage signals used as the input of transformer-based deep learning models allowed for real-time fault detection. A transformer-based deep learning model overperformed of CNN model as it is utilized global content and long-range dependencies of segmented data. Even though there are limited fault-related data points, the proposed method enable accurate fault detection using data acquired under limited PMUs conditions, indicating this method has the potential to be applied in the actual power system fault detection scheme. The majority of data used in the scheme in the study were simulated under normal condition. If accuracy was calculated using the entire dataset, it may result in the higher accuracy value that does not reflect the real-time fault detection capability of proposed deep learning model. To address this issue, a new evaluation method was defined to assess the real-time fault detection performance, especially the accuracy, and the fault detection time was calculated using only 5 data points before and after the fault onset. This approach provides insight into the accuracy and speed of the proposed deep learning model in detection faults in power system. Overview of analog and mixed signal circuits. Analog circuits proves continuous signals with mixed signals circuits integrate both analog and digital components. Faults can arise from various sources, including components and degradation, environmental factor, and design flaws. Understanding the equivalent characteristics of these circuits is crucial for effective fault detection strategies. Methodologies for fault detection techniques such as signal integrity testing and parameter monitoring are employed for the fault detection. Advanced algorithm including machine learning can enhance fault identification capabilities. A combination of hardware and software solutions can optimize detection processes. Real-time monitoring. Modern system utilizes oscilloscope spectrum and analyzes and detect fault detection. Hardware software platforms can visualize data and provide real-time alerts to operate. Integrated of IO technologies can utilize remote monitoring and diagnosis. Diagnosis techniques. Diagnosis involves isolation the fault and determining in root causes. Techniques such as signature analysis and simulation based diagnosis are commonly used. Utilizing historical data can improve the accuracy of fault diagnosis over time. Implementation challenges. Real time fault detection system face challenges such as high speed data processing and signal noise. Ensuring systems reliability while maintaining accuracy can be complex in mixed signal environments. Additional compatibility with existing infrastructure may pose integration difficulties. Case studies and applications. Various industries including technology, telecommunication, and medical devices benefits from these systems. Case studies illustrate the effective of the real-time fault detection in enhancing operational efficiency. Lesson learning from these applications can inform future developments in fault detection technologies. Future direction and innovation. The future fault detection lies in the integration of AI and machine learning for predictive diagnosis. The continued advancement in sensor technology. Thank you for giving this wonderful opportunity.